Hi gang, Math 5500. Well, I got to laugh at myself. I said in the previous video that I wanted to keep my videos around 20 minutes, and I thought the previous one was about 20 minutes. Finished up, it was like 9 minutes. So, hey, good for you. Um, but I'll tell you what, there was a lot that was covered in those 9 minutes. So, what I want to do now is I want to put all this to work, and let's see how a test of hypothesis would be carried out and how we would calculate a confidence interval. So again, right now I'm going to focus on inference for beta 1. And of course, B1 is the estimate. Our focus is on the distribution of the B1s. And from the previous video, we saw that they will be normally distributed with a mean equal to beta 1 and a variance equal to well, we'll calculate it by taking the mean square error over the sum of the deviations for x. And just put out here, tattoo to the brain that the mean square error is the sum of the errors squared over the degrees of freedom, which will be n minus 2. Now, first thing I need to do is calculate B1, and I'm going to do that by taking the sum of the product of the deviations over the sum of the deviations for x squared. Getting a little sloppy here, not using the subscripts just because I don't want to. There you go. So I'm going to do that for GPA and ACT. Again, the goal here is to predict GPA from ACT. So I want to calculate the numerator just as before. So I want to take the x's, which are ACT minus the mean ACT times the GPA minus the mean of the GPA. So that's going to give me my numerator. The terms for my numerator actually gives me 707 of them. I think no, 705 of them. My bad. Denominator, I want to create the deviation squared for x. So again, x is my ACT. And I want to square those. All right, so let's just save this as B1. So my estimate for beta 1 is the sum of the numerator divided by the sum of the denominator. So 0.0578 is the estimate for beta 1. Now, let's move into the inference setting. And what I want to do is I want to take this sample and I want to test that we have what I would call statistical significance. And I want to test this against beta 1 not equal to 0. Statistical significance. Okay, the null hypothesis here is we're assuming that there's no linear relationship between x and y, between ACT and GPA. In other words, the slope of the population model is equal to 0. We want to see if there's evidence against that at the 0.05 level to where we reject H sub O and conclude that the beta 1 is not equal to 0. If we conclude the beta 1 is not equal to 0, then we're going to want to dive into the confidence interval and say, well, if it's not equal to 0, just what exactly is it? and the standard, the line in the sand we'll probably use, is the 95% confidence interval. So I know that to test this, that the test statistic is going to be the beta 1 estimate minus the claim for beta 1 over the standard deviation for the beta 1s. Well, guys, this is easy. This is easy because we're testing the claim that's equal to 0. And this is going to take just a little bit of work. So the key to finding this is to find the variance. And, we already have the deviations squared, right, the sum of those. All we have to do now is find the mean square error, which is this term right here. So what I would want to do there is, I'll tell you what, let's just go ahead and calculate beta 0, which we're going to need. So we need the mean of the y's, which would be GPA minus the B1 times the mean of our x's, which would be ACT. So beta 0 is going to be equal to 1.55. Okay, so what we need to do now is we need to find the observed y's. All right, so I want to find the errors. Actually, I want to find the errors squared, don't I? So the errors squared are going to be the observed minus the predicted. So the observed is going to be the GPA. And the predicted is going to be it's going to be B1 times the ACT plus B0. And we want to square those. So then the MSC is going to be equal to error squared divided by the length of the ACT minus 2. So, okay, what did I do wrong there? Okay. I have to sum those, so I made a big boo-boo there. So the MSE, first mistake I've ever made. I don't think you're going to believe that. Error squared divided by, yeah. All right, so the mean square error is 0.3493, much better. So we know that the sum of the deviations was what we used before. Some of the deviations we had is numerator, right, or denominator. So the variance B1 is going to be the mean square error divided by the denominator. I don't know, I'm getting confused. Yeah, there we go. So the standard deviation for B1 will be equal to the square root for the variance of B1. Finally. All right. So just for the heck of it, let's see what the standard deviation for B1 is. So what I can do now is I can do my test statistic. And again, it's the numerator. So where I am, I'm back to this point. So the standard deviation for B1 was 0.00555. So my test statistic is going to be the B1 divided by the standard deviation for B1. So the test statistic is 10.4149. Now, to find the p-value, what I need to do is, since we're testing a two-tailed test, I need to find the area to the right of 10.415 and to the left of negative 10.415. Two-tailed test means we have two tails. So to find the area there, I'm going to use PT, test stat. Degrees of freedom would be length ACT minus 2, because that's the t distribution that I'm finding. So again, PT, that's just for R, it's finding the probability, this area, for the t distribution with the degrees of freedom specified. Easy for you to say. So, oh my bad. We would need the negative of the test statistic. And what it's saying is there's just not a lot of area there. And because of symmetry, there's not going to be a lot of error there either. So my p-value is extremely small. I have to add the two areas together, so when I add not much plus not much, I get not much, okay? So again, it's very small, and we would report this as just p less than 0.001. Now, once we get this, we can actually test it out. We can set up our model and do a linear model and predict GPA from ACT. And take a look at our model. And look at a summary of our model. Now you're going to see some things that look awful familiar. First of all, you're going to see our estimate, 0.0578, which is exactly what we got right here. You're going to see a standard error, which is 0.055, which exactly what we got for a standard deviation. You're going to see a t-value, which is our test statistic of 10.41, which is what, I don't think I wrote that down, did I? But anyway, we got it right up here, 10.415. And our p-value is extremely small. 2e, put in 15 zeros, and there you go. Something kind of cool, residual standard error, 0.591. Have we seen that anywhere? I believe we did. Well, no, we didn't calculate that. I calculated that in a previous video. And the ANOVA output, we'll talk about that in the next lesson. Now, moving forward with the confidence interval, the confidence interval is going to be our, let's see, lost my train of thought here. Confidence interval is going to be our beta 1 plus or minus our t critical with degrees of freedom n minus 2. I forget, what was it? We had 705 sample size, so 703 times the standard deviation. So again, beta 1, our estimate, 0.0578 plus or minus. Now, the t critical, what we're doing is we're examining the probability distribution, the t distribution, degrees of freedom 703. And what I want to do here is I want to focus on a 95% confidence interval. So that tells me that 95% of our samples will be between two bounds. So I'm obviously missing 5%, so half of that 5% will go in this tail, and half of the 5% will go in this tail. So in this distribution, I'm looking for the value, the line in the sand, that separates the bottom 2.5% with the rest of the distribution. Well, we do that using the QT function, and the first thing I enter is the area to the left. So I want 0.025. And again, I have t distribution, degrees of freedom 703. So my QT will give me my t critical equals plus or minus 1.963344. So this will be the negative of that, and this will be the positive, because, ladies and gentlemen, the mean of the t distribution is equal to 0. All right. Really, we have a very easy calculation here, don't we? So again, I didn't finish this out, but we have 0.0578 plus or minus 1.96344 times the standard deviation for, here we go, 0.00555. All right, really easy to do with a calculator, but also easy to do with this. So 0.0578 minus 1.963344 times, what did we call that before? Just SDV1. So the 95% confidence interval for B1 will be from 0.047 to 0.069. So we are there's a 0.95 probability that this interval will capture the population slope for the population model. All right, so if we were to take, be able to examine all of our population and not using inferential techniques where we're taking a sample and trying to generalize from that one sample. So we can do that by taking, creating the confidence interval. Now, something you can do, confidence interval of your model, I always hesitate to, at least you guys can't throw anything at me. You can see that for ACT, which is your B1, that let me make sure we're looking at the same place, that your 95% confidence interval is given. All right. Now, let me grab a sheet of paper, go on just a little bit. I'll tell you what, I'm going to end the video here, and we'll take up with the next video. All right, take care.